A black hole with a mass that could be 2 to 4 million times that of the Sun is incredibly powerful, but thanks to research conducted over the past few decades, we've gone from knowing virtually nothing about them to uncovering more and more, sometimes in surprising ways. Recently, researchers, including those at the Kaku Institute, reported that they've managed to peer inside a black hole. Black holes are a phenomenon that has fascinated physicists for more than a century. These massive entities that, while our understanding of gravity remain largely invisible to us, this new data has shed light on aspects of the universe that science may have previously overlooked. Let's explore black holes and learn more about the vast and inspiring universe that exists within space. But first, it's important to understand the fundamentals of what black holes are. Although the concept of black holes is well known, there are still a lot of unanswered questions. When Albert Einstein published his general theory of relativity in 1916, predicting the existence of such objects, the idea of a black hole became theoretically possible. However, until scientists discovered compelling evidence supporting the existence of black holes in the 1960s while studying the binary star system Cygnus X-1, astronomers discovered an unusually bright blue star emitting X-rays. This star wasn't a normal celestial body. Rather, it was orbiting around a mysterious massive object. After more investigation, it became evident that the X-rays weren't just floating around in space, but were being drawn toward the dark entity, confirming the existence of black holes. This was a groundbreaking discovery that demonstrated that black holes were real phenomena rather than just theoretical concepts. It is impossible to overestimate the importance of this finding. It indicated the existence of a whole new class of things in space that needed immediate and careful investigation. The first known black hole, Cygnus X-1, is situated in the Cygnus constellation, approximately 6,000 light-years from Earth. It is many times brighter than our Sun and has a tremendous gravitational pulse so strong that not even light can escape it. This renewed focus on black holes was the result of researchers from all over the world. This is the reason it's called a black hole. The idea of a black hole, which is an area in space where the gravitational pull is so strong that nothing, not even light, can escape it, is both exciting and terrifying. The study of black holes is not only fascinating but also necessary, since everything that approaches one is inevitably sucked in and condemned to be lost forever. However, are we in any imminent danger risk posed by them? Although the nearest black hole is around 500 light-years away, this distance still prompts concerns about possible dangers, and the full extent of black holes is still being discovered. Following the discovery of Cygnus X-1, scientists started looking for further black holes. The number of black holes in our Milky Way galaxy alone is thought to reach up to 100 million. However, finding them is still a tough task. According to estimations, there are millions of them in our galaxy, highlighting the significance of researching these mysterious objects. The main issue with black holes is their tremendous gravitational pull, which is so powerful that it draws everything, even light, into itself. The singularity, the black hole's core, is where all matter that enters it is compressed into an infinitely dense point. Black holes function as cosmic vacuum cleaners, consuming everything in their vicinity. If someone were to fall into one, they would be gradually compressed and stretched until they were reduced to a singularity. This process is extremely slow, meaning that the person would die long before the final, irreversible stage. But despite the apparent danger, black holes are so common that they cannot be ignored. In 2019, scientists made history by taking the first clear image of a black hole, the supermassive black hole at the center of the M87 galaxy. The image was taken over several nights, and with each exposure, new information was gained. The data was then meticulously assembled to provide a clearer picture. The most remarkable is it was discovered that a black hole is made up of three different layers rather than simply one empty area. The event horizon, the first strom, designates the place which once crossed, always draws an item toward the black hole beyond which nothing can return. The photon sphere, the second layer, is where light is locked in orbit. Any light that reaches this area is drawn into the gravitational pull of the black hole and is unable to escape. The singularity, which occurs when matter is compressed to a single point in space-time, is the last layer in this environment. The rules of physics as we know them cease to apply. Unlike other objects in the universe that we can study directly, black holes can only be studied indirectly by researchers using observations of the radiation emitted by black holes and the gas and dust surrounding them. This breakdown of the laws of physics is one of the many reasons studying black holes is so difficult and fascinating. What's even more fascinating is that each black hole behaves differently, even though they tend to share the same basic structure, because anything that crosses the event horizon is drawn into the singularity and crushed to an incredibly small point. It is impossible to send a probe into a black hole. This poses a serious limitation for scientists because they are unable to study black holes in the conventional manner and must instead use two-dimensional models to comprehend these three-dimensional objects. Additionally, black holes vary in size and form, which makes research on them much more difficult. When a star runs out of fuel, it can no longer produce the energy required to oppose the force of gravity, causing it to implode. If the star is massive enough, this collapse continues until the star reaches a singularity. This is one of the most well-known theories that scientists have developed to explain how black holes form. NASA researchers have concentrated on a particularly potent galaxy, M87, where they saw a huge whirlpool of hydrogen gas rotating at an incredible 1.2 million mph. Despite the tremendous forces at work, the gas didn't break apart, leading scientists to believe that there must be a massive object at the galaxy's center holding everything together. In 1963, they discovered that this object was a black hole that weighed billions of times the mass of the Sun. The mathematician Roy Kerr of New Zealand developed a model for revolving black holes using Einstein's equations. According to K's theory, a spinning black hole may create an accretion disk or ring of fire, rather collapsing into a single point. This disk would revolve so quickly that the external forces would cancel out the gravitational collapse. Additionally, the idea of the Einstein-Rosen bridge or wormhole was presented by K's work. Wormholes are hypothetical tunnels that might theoretically interconnect alternative worlds or two distant locations in space-time. According to Einstein's theory of special relativity, the speed of light is the ultimate limit for how fast anything can travel, which creates a barrier for using wormholes for faster than light travel. However, even if wormholes do exist, it is unlikely that we would be able to travel through them anytime soon. The idea of wormholes has fascinated scientists for decades. If black holes are indeed connected to wormholes, they could offer a shortcut through space-time that would allow travel between distant regions of the universe or even between different times. However, wormholes remain an intriguing topic for theoretical study because if stable, they would provide a way to travel over enormous stretches of space or perhaps to other eras. A few physicists also hypothesize that wormholes may provide a means of time travel, but getting through one would be very difficult since they would probably be unstable and encircled by strong gravitational and radiation fields. To fully comprehend the characteristics of black holes, physicists will have to create a cohesive theory that incorporates quantum mechanics with Einstein's general relativity theory. Superstring theory is one intriguing contender for this theory, which postulates that the basic elements of nature are really microscopic vibrating strings. These strings may be able to explain a number of the universe's puzzling occurrences, such as the creation of wormholes and black holes. Superstring theory also suggests that black holes, wormholes, and other exotic solutions to Einstein's equations may arise due to the bending of space-time by these tiny strings. Despite its promise, superstring theory necessitates the existence of additional dimensions of space-time that are too small for us to detect, but research into black holes and their mysteries continues to push the boundaries of our understanding. One of the most innovative theories regarding black holes is the theory of Hawking radiation, which was put forth by physicist Stephen Hawking in 1974. Hawking theory postulates that black holes are not entirely black, but rather emit faint radiation due to quantum effects near their event horizons. This radiation could cause the black hole to gradually lose mass over time, eventually leading to its evaporation. Despite being hard to detect because of its weakness, Hawking radiation provides important information about how black holes behave and their function in the cosmos. Additionally, black holes provide a unique laboratory for researching how gravity and quantum physics interact. The harsh circumstance is close to a black hole for physicists seeking to create a theory of quantum gravity. Singularities are a crucial field of study, since here is where both gravitational forces and quantum effects interact. Black hole research may also hold the conditions around a black hole, may provide clues about the universe's beginnings. According to some theories, if wormholes are real, they may also offer a means of exploring large areas of space-time, opening up new avenues for interstellar travel. Despite the fact that these theories are still theoretical, they continue to motivate researchers to investigate the most profound issues regarding the nature of our universe.